What if you could get high-quality images from a generative model in just one single step? No pre-training, no tricks, no waiting around. Meet Meanflow, a new way to generate images that ditches the usual step-by-step dance of diffusion models. Instead of tracking instantaneous velocity, it learns to follow the average velocity, kind of like finding the straightest path from A to B, rather than wobbling through every stop along the way. This simple shift unlocks some serious speed. We're talking ImageNet quality generations, trained from scratch, and beating previous one-step models by a mile. Ready to unpack the magic behind this single-step wonder? Let's dive into the flow, the Meanflow.
Let's kick things off by setting the stage. The goal here is to generate data, like images, using just one step. Yep, one-shot generation, instead of the usual many-step processes we see in diffusion models. Now, in typical methods like diffusion or flow matching, what we model is something called instantaneous velocity. Think of it like steering a car and adjusting your direction every second. It's precise, but it takes time. The authors flip that idea and instead ask, what if we just focus on the average velocity? That's the total displacement over a time interval, divided by how long that interval is. So instead of controlling every turn, you just know where to start and where to end, and draw a straight line between them. That's the core idea behind this new framework, which they call Meanflow. And here's the neat part. It doesn't rely on pre-training, distillation, or any kind of curriculum learning. It's trained from scratch and runs with just a single function evaluation, what they refer to as 1NFE, short for number of function evaluations. Take a look at Figure 1, which you'll see is that Meanflow models hit much lower FID scores compared to previous one-step methods. That means higher image quality. And they're doing it in one go. For example, IMM, a prior model, needs 2 evaluations per sample. Meanflow matches or beats it with just 1. So we're starting with a big shift. Rather than following every twist and turn like flow matching, we model the average journey. And the early results? They suggest it works. Let's keep building on that idea. The whole premise is about simplifying how we train these generative models. Rather than estimating velocity at every moment, which is what flow matching does, the authors propose focusing on the full journey, what's called average velocity. They train a neural network to predict this average velocity between 2 time steps. And to do that, they use a loss function that enforces a mathematical relationship between average and instantaneous velocities. Here's the interesting part. That relationship comes from basic calculus. No heuristics, no handcrafted tricks, just definitions. This simplicity also brings a bonus. Classifier-free guidance, CFG, is often used to improve sample quality, but it usually doubles the computational cost. With this setup, integrating CFG becomes easier and cheaper. We'll dive into that more later. Now, to put all of this in context, the paper reviews prior work. Diffusion models and flow matching methods all aim to generate data by transforming noise into structure, often using many tiny updates along a path. And sometimes, they add distillation or curriculum learning to speed things up. Meanflow skips all that. Before moving on, the paper takes a moment to explain how flow matching works. Picture blending an image and noise using a recipe that changes over time. The velocity is just the rate of change in that blend, like how fast you're shifting from noise toward the final image. This helps frame why the average velocity idea is not just simpler, but potentially more powerful. Let's dig into that flow matching setup a bit more. The velocity field we're trying to learn tells us how data points move through time, but there's a problem. At any given time step, the same point could have come from lots of different combinations of data and noise, so the velocity at that point isn't unique. Take a look at Figure 2. On the left side, you've got what's called conditional velocity. Each sample has its own trajectory depending on its data-noise pair. That's why there's a bunch of different arrows, even at the same point in space. On the right side, they average over all of these possibilities. This gives you the marginal velocity, which is smoother and easier to work with during training. The model tries to learn this marginal velocity, and once it does, we can use it to generate new data by solving a differential equation. That just means we start with noise and simulate its transformation over time using the learned velocity. Now the authors propose a switch. Instead of tracking every moment, they go back to that core idea, average velocity. It's just the net change between 2 points, divided by how much time has passed. At the bottom of the page you'll see the equation that defines it formally, but the takeaway is simple. This shift gives us a smoother, more stable training process and lets us skip all the intermediate steps. In other words, instead of following the trail step by step, we just jump straight to the destination. Now we're getting into the heart of how this works. That visual at the top? It nails the concept. Instantaneous velocity follows the twists and turns of the path, but average velocity? It goes straight from start to finish. It doesn't care about the wobbles in between. The goal is to teach the model to learn this straight line movement. But here's the challenge. How do you compute average velocity in a way that a model can actually learn from? That's where the Meanflow identity comes in. It starts from the basic definition of average velocity as an integral over time. Then they take the derivative of that integral and apply the product rule from calculus. What they get is an identity that links three things: the average velocity, the instantaneous velocity, and the time derivative of the average velocity. This new equation becomes the cornerstone of training. But that time derivative? It's a bit tricky. So the authors break it down further using partial derivatives, essentially measuring how the average velocity changes over time and space. By doing this, they get an expression that's compatible with tools we already use in training neural networks. This entire move turns what could have been an intractable problem, integrating over time, into something that fits neatly into a standard training pipeline. Now that we've got the Meanflow identity and a way to compute its components, let's talk about how training actually works. The model predicts average velocity between two time points. To guide that prediction, they compute a target using the Meanflow identity from earlier. Specifically, it uses the known instantaneous velocity and how the network's output changes over time. That's enough. You don't need to evaluate any integrals. Here's where it gets clever. To compute that time derivative efficiently, they use a Jacobian vector product, or JVP. This is a standard trick in libraries like PyTorch and JAX. And the best part? You only need a single backward pass to do it. It's just as cheap as normal backpropagation. They even mention that in their JAX implementation, the overhead is under 20%. Pretty efficient. The whole training process is wrapped into algorithm 1. You sample 2 times, create a noisy point, compute the velocity target and its derivative, then minimize the loss. It feels familiar if you've worked with flow matching before. Just a different target. Now for sampling. Once the model is trained, generating a sample is super simple. You start with noise and subtract the average velocity predicted between time 0 and time 1. That's algorithm 2. One step. That's it. And while the paper focuses on this one-step approach, it's worth noting that this framework could also support multi-step generation if needed. Let's talk about classifier-free guidance, CFG. It's a common way to improve the quality of generated samples, but normally you have to pay for it. You run the model twice, once with the class label and once without, and then mix the results. What the authors do here is bake CFG into the Meanflow framework without needing 2 passes. They define a new velocity field that blends the class conditional and class unconditional fields. A weighting parameter controls how much influence the class label has. So if the weight is high, the model strongly follows the label. If it's low, it generates more freely. Then they plug this blended velocity into the same average velocity formulation we've been using. They compute a new target for training, just like before. But now it's guided by the class information. And the training procedure doesn't change. It's still the same loss function, the same gradient computation. At sampling time, you only need 1 pass. Just use the blended velocity field, and you're done. No doubling compute. No model juggling. Just straight up CFG, with the same efficiency as before. That's a smart way to make guidance cheap, and keep everything fast and simple. Now we dive into some of the design choices that shaped training. First up, loss metrics. They go with a basic squared L2 loss, but also try tweaking it with adaptive weighting. That means giving less weight to big errors, so the model doesn't overreact to noisy outliers. Next is how they pick the time steps used for calculating average velocity. They sample 2 time points, R and T, from different distributions, sometimes uniform, sometimes long normal. The goal is to mimic realistic timing variations. Then there's the question of how to feed those times into the network. Since the model needs to understand what R and int are, they test different ways of encoding that info. For instance, instead of passing both R and T separately, they sometimes just give the difference, T minus R. Turns out, that works pretty well. From here, the paper moves into experiments. The models are trained on ImageNet at 256 by 256 resolution using a vision transformer-based backbone. A tokenizer converts the images into latent space, and everything is trained from scratch. Then they test different setups through ablations. One experiment shows that if you don't vary RNT, performance drops. Another shows that computing gradients the wrong way kills performance. All these tweaks make a difference, and they all come back to how you structure time in training. This part really breaks down which of those training choices matter most. Check out Table 1A. If you always set R equal to T, you're basically doing vanilla flow matching, and the FID shoots up over 300. But if just 25% of your time pairs are different, FID drops to 61. That's the sweet spot. Now look at Table 1B. This shows how crucial it is to compute the Jacobian vector product the right way. If you mess up the tangent direction, the model can't learn properly. But when you get it right, performance is optimal. Table 1C focuses on how you represent the time inputs. Feeding in the difference between R and T works better than feeding both individually. It's a small detail, but it gives a real improvement. For sampling time points, Table 1D compares different distributions. Log-normal distributions work better than uniform ones. They give a more realistic spread of time intervals, which seems to help. Then we've got Table 1E. It explores how tweaking the loss function affects results. Adaptive loss weighting, especially when tuned with a power of 1, gives the best outcome. Go too far off that value, and performance drops. Finally, Table 1F covers classifier-free guidance. Without it, FID is about 61. But as you increase the guidance strength, performance improves dramatically, down to around 15. Put it all together, and you can see how much each piece of the puzzle matters. Gradient direction, time sampling, input representation, loss weighting, and CFG strength all shape how well this one-step method works. Let's wrap it up by looking at how this performs at scale. Figure 4 shows how FID drops as the model size grows. From B to XL, larger Meanflow models get better and better, even though all are still using just one NFE. That means they scale well. Look at Table 2 on the left. It compares Meanflow to other one-step and two-step models trained from scratch. The XL version hits an FID of 3.43, with only one function evaluation. If you allow it, 2 evaluations. Meanflow-XL to it goes down to 2.20, matching top-tier many-step diffusion models like DIT and SciT. Table 2 on the right compares Meanflow to models like BigGAN, StyleGAN, and ADM. Despite being simpler and faster, Meanflow still performs competitively, often with fewer evaluations and no distillation or tricks. Then there's Table 3, which covers CIFAR10. Even with this smaller dataset, Meanflow holds its own. It hits an FID of 2.92 without any special preconditioning. That's right in the ballpark with elucidated diffusion models that use much more complex setups. At the bottom, the paper ties this all back to simulation. The average velocity idea isn't just about generative modeling. It connects to a broader theme in physics: modeling change across scales. It's the same concept used in simulations of systems that evolve over time or space. So while this method targets one-step image generation, the ideas behind it could go far beyond that. Thanks for joining us today. Happy exploring!